Alright, so we're going to go over the last 20 questions from this TMSCA 10 math test from this year. Okay, so number 41, so we're getting into calculus content. We want to know which of these integrals is equivalent to this limit expression of the integral. And so the way that we define an integral as a limit, so we have some integral f of x from a to b, we can write that as the limit as n approaches infinity of the summation from k equals 1 to n of delta x times f of x sub k, where delta x is equal to the difference between the upper bound and lower bound divided by n, and x of k is equal to a plus delta x times k. And so what does all that mean? It's just like a bunch of letters. Okay, so the idea is when we have an integral, so say like this, between two bounds a and b. Okay, so as n goes to infinity, think of n as the number of slices we're making. So if we had one slice, like we're approximating this area as one rectangle. So I'll use a different color. So something like this. That would be if n is 1. Now this area would be more precise if we had two rectangles. That'd be n equals 2. And delta x is the width of these rectangles. So, because, it's the difference between these divided by how many rectangles. So if I had 3, so n equals 3 here, and I have 3 rectangles, my area would be even more precise. With each of these lengths, these delta x's, being b minus a over 3, or over n, right? So the idea is we take infinitely many slices, so as n goes to infinity, we have all these tiny, tiny rectangles. They're infinitely small in their width. We'd have the exact area. And so that's where this delta x part comes in. And really what this summation is, it's just width times height. We're just adding the first to the nth rectangle, so all of these rectangles, and getting all of their areas. We're just summing the areas of n rectangles, which are infinitely small in their width. So the f of x of k part, so x of k tells us the height of the kth rectangle. So when k is 1, our height, or first our x of k is going to be our initial value, or a lower bound, so a, plus a little delta x. Let's pretend this is the rectangle. It's definitely smaller, but just for an example. So it's like a plus a little step forward of delta x. And so this is our x of k. And when we do f of x of k, we get the height. So like that. Whoops. Okay. So that kind of explains like how this formula, I guess, or definition here works. So you gotta know this. Well, actually, all of this. Okay, so returning to our problem, if I kind of like substitute in these values, so it's going to look a little complicated, but it's going to help us out. So I can write this as the limit as n goes to infinity of the summation from k equals 1 to n delta x, which is b minus a over n, times f of x of k, which is a plus, well, delta x was, again, b minus a over n times k. So this is our expression, like our kind of a complete expression. Now let's compare this with what we got in the problem. So our problem, it lists out the sum as 2 over n times 2 plus 2, I'm going to write it as 2 over n times k. So it kind of looks more alike. And so what information we can get from this is that the difference between our upper and lower bound must be 2. And so right away that eliminates answer choice B, because these are 4 apart, and answer choice E, because these are also 4 apart. Okay. So from there, the only kind of like a mystery we have left is how do we write, or how do we determine what the function is? Because in this one we have x dx, this one we have 2 plus x dx, and these also have different upper and lower bounds. So how can we determine? Well, we know that f of a plus, and we still know what a is, but we know what a minus b is, so I can write this. We know that this expression must be equal to 2 plus 2 over n times k. And so let's think, like, what value of a and what function would get us this result. So if a is equal to 2 and f of x is equal to x, then f of 2, because 2 would be a, f of 2 plus 2k over n must output what we just have in here, which would be 2 plus 2k over n. And that is equal to what we want. So this solution right here is valid. And so the only answer choice like that is answer choice A, which has that lower bound of 2 and has a function of x. So A must be our answer. Now, there are different possible solutions as well. Another solution that would have worked is if A was 0 and f of x was 2 plus x, because then if we took f of, would be 0 plus 2k over n, we would get 2 plus 2k over n, which would also be valid. But notice how none of the integrals look like from 0 to 2 of 2 plus x dx. This is not an answer choice. If it were, that would also be correct. We have one that's similar, answer choice D, but instead of being from 0 to 2, it's from 2 to 4, which would give us the wrong answer. So A is the correct answer. So the major takeaway for this question is know how to write your limit, or know how to write your integral as a limit expression. Sounds kind of a long problem, but it's a good one. It's a good calculus problem. So, moving on to question 42. Okay, so it's another calculus question. So, we have a piece of cardboard that measures, let's make it more similar. Yeah, it looks like 4 by 5. So 4 foot by 5 foot, and it's folded up to create an open-topped box by cutting a square out of each corner. So we're making a cut here, 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 and here. So it looks something like this. Okay, then we're going to fold it up so it looks something like this. Okay. And so we want to know what the maximum volume that can be created from this 5 by 4 is. Okay, so this is an optimization problem. So here's how we'll solve it. So let's call the little piece that we take out, the square piece, let's call the length of that square piece x. So then this length is 5 minus 2x. And this height right here is 4 minus 2x, because there's an x taken out from here and here. So if that's the case, then our box is going to have a length of 5 minus 2x, a width of 4 minus 2x, and a height of x. And of course, x can be like a very small square, it could be like a very big square. It's variable. But we can express what the volume of the solid is going to be. You just do, the volume formula, length times width times height. And so we can write the volume as 5 minus 2x times 4 minus 2x times x. So this is our volume. And it's dependent on whatever our x is. So I'm going to call it v of x. But what you can do, if we want to find the maximum volume, well, we've got a function that describes the volume dependent on x. So if we want to find the maximum volume, we're just going to find the maximum of this polynomial. And so you're going to go to your graphs page on your TI Nspire, and you're going to write out this function. So after you graph it, and also note that the only possible values x can be are between 0 and 2. Because if x was greater than 2, we'd have a negative length here, which is like impossible. So x can only be from 0 to 2. So with that in mind, we're going to look for the maximum value between 0 and 2. We're going to go menu 6, menu 6, 3. So we're going to find our maximum. This is the function on the calculator that lets you find your maximum. So what it should look like once you graph it should be something like this. And so after you do menu 6, 5, or no, menu 6, 3, you're just going to tap like some area here to write your lower bound, and some area here to get your upper bound. And it's going to tell you what the maximum point within this bound is. So that's going to be up here. The calculator tells me that the point I have here is 0.736, comma 6.56. Now remember, we want to know what the maximum volume is. So that would be our y coordinate. So 6.56 is our answer. So that will be answer choice A. So yeah, for optimization problems, what you usually want to do is you want to write your problem in terms of x and just graph to see like the maximum if it's asking for like what's the maximum amount something can be, or you can write it as a minimum. So you can write your function and look for the max or min, depending on, of course, what the problem's asking for. All right. So, moving on to question 43. Okay, so the function f of x is a differentiable function, and it's defined like this. So it's a piecewise function, meaning like, for example, like if I had a piecewise function like f of x equals, I don't know, say x for x less than 0 and like x squared for x greater than or equal to 0. That means like the left side of the graph before 0 is going to look like, y equals x. And after 0, it's like it switches and it becomes like this parabola. The piecewise functions aren't too bad to deal with. But this question, it's got like a calculus twist to it. So let's write out the function. So f of x is equal to, is equal to 6x squared plus dx for x less than 3, and x squared minus d for x greater than or equal to 3. And we want to know what c plus d is, given that this is a differentiable function and it's defined. Okay, so for a function to be differentiable, two things need to be true. So the first thing that needs to be true is that the values here, so values at, well, this case, like if I were to call this value right here like a, because usually it's defined as like x is less than a and x is greater than or equal to a. So values at a have to be equal. So this condition makes it so that the equation has to be continuous. So what that would look like is it makes sure that, okay, this is a graph you would not want. So if you got like a hole there, and then your graph looks like that. So that's not what we want. What we do want is for them to basically be connected. So something like this. So you see how like there's not like some jump here? They're connected at that point where it changes. That's what we want. And so that's what that first condition means. Okay. So then the second condition is that, okay, well, let's call this first function f of x. Let's call this second function g of x. So I can rewrite this as like f of a has to be equal to g of a. The second condition is that f prime of a must be equal to g prime of a. So the derivatives have to be equal at that point where these two graphs come together. So an example of what we wouldn't want is, let's say I have a straight line here, and then I've got like this parabola. That's not what we want because the slope here is super different from the slope here. It's not the same. What we would want is for it to kind of like transition nicely. So like these slopes are equal at this point where the functions change. So basically what the second condition makes sure is that the transition is smooth. So these are your two conditions that you've got to know for your piecewise function to be differentiable. So this makes sure it's continuous, and this one is differentiable. Okay, so then how do we do this? Well, to satisfy the first condition, we can write c times x squared plus d of x plus d times x is equal to x squared minus d. At the point x equals 3, right? So we're going to substitute all of these x's with 3. So we have 9c plus 3d equals 9 minus d. So this is our first equation. And so to satisfy the second condition, we're going to take the derivatives of both equations. So using the power rule, we get 2cx plus d equals 2x. And so again, this is going to be at the point x equals 3. So I'm going to substitute these x's with 3's. And so we get 6c plus d equals 6. And so we've got two unknowns, and they're related to each other by these two equations. So that's a sign that we need to write a system of equations. So on your calculator, you can go menu 371, and you can write the system of equations. And so we get that the value of c is 1, and the value of d is 0. So these are the two values that satisfy this condition such that this piecewise function, f of x, can be differentiable. So we wanted to know what c plus d is. We're just going to add 1 plus 0, which is 1. So that's our answer. So it's another longer calculus question, but the main takeaway is you gotta know the conditions to which a piecewise function has to follow so that it's differentiable. All right, so problem 44. Consider the function g of x defined as being equal to this integral if this variable upper bound x for this equation. Okay. Which of the following values of x does the function maintain a relative maximum on the interval from 0 to 2.5. Okay, so this is actually not too bad. So if you think about this question's asking. Okay, so we have this function in the integral. So here's a thought. We want to find the maximum of g of x. So just looking at, well, let's call this equation right here f of x for now, or f of t. In order for g of x to have a relative maximum, then what must be true of f of t? So I'm going to write two graphs. This is going to be f of t and g of x. So if g of x has a maximum, relative maximum somewhere, it would look something like this. So here it has a maximum. So what that would look like, for example, on f of t, and this is not the exact, like what you'd get if you graphed it. I'm just making up this random line. But what this would mean is that for your function f of t, again, the integral is just like the area, right? Let's call this a. So the area is, getting more and more positive, or it's starting off really positive. It's growing a lot, as evidenced by this sharp tangent line, kind of towards this area of g of x. But then it's going to start accumulating less area over time, so the slope's going to slowly decrease until we hit a point where f of t crosses from being positive to being negative, and then it starts accumulating negative area, which brings this value of g of x down. And so that's the key insight here, is that wherever there's a relative maximum for g of x, at that same x value, we're going to see f of t cross from the positive y value to the negative y value. And so f of t was sine of t squared minus 1. So we're going to graph this on our graphs page. And from 0 to 2.5, it looks something like this. So notice, again, we don't want the zeros necessarily, because if we chose this as our answer, we'd be wrong. What we want is we want the 0 where it goes from being positive to being negative. And so that would be this 0 right here. And so if you were to isolate that point on your graphs page, so you can do like menu 6.1, you get that this point is 2.04, comma 0. And so that is the exact point where g of x will experience a relative maximum. And so the answer choice that's closest is answer choice E. So you gotta think in terms of, like, in order for g of x to have a maximum, what must be true of f of t? That's a fun calculus question. Here's a quick one. Okay, so for question 45, we have a particle that moves along the y-axis with this velocity defined by this equation. we want to know how many times does the particle change direction on this interval. So this is actually a really easy question to think about. So again, this is giving us the velocity over time. So in order for you to change direction, that means you change from having a positive velocity, you cross over to having a negative. So this would be a change in direction. Or if you cross over from being negative to being positive in your velocity. Okay? It's like if you turn around. Okay? So all we really need to do in this question is we need to graph this function, f of t, and see between -2 and 4 how many zeros there are, and that's our answer. So if we graph this from, looking at the -2 to 4, we get a graph that looks somewhat like this. And it's going to have 1, 2 zeros. So here, this negative side of the x-axis, it's having a positive velocity, and then it's dipping and becoming negative after this point. So that's one change in direction. Why isn't that drawn there? Okay. And then here, it's going negative, and the velocity starts turning positive. So that's a second change in direction right there. And so there are 2 times that the particle changes direction on that interval. So 2 is our answer. So you just want to look at how many times that velocity changes, or how many zeros there are when you graph the velocity. Okay, so moving on to 46. Another calculus question. So we've got this graph right here. So this graph should already be signaling that this is a logistic model. Logistic models, they're characterized by they look like this, and then they flatline at some carrying capacity. And so a logistic model, when defined like this, so like dp over dt, it's equal to some constant k times p times 1 minus p over k. Or not k, my bad. P over L. And so what do these numbers mean? Okay, so again, like with the logistic model, you see that it usually tapers off at some maximum value and just stays there. That value right there, that value L, right, is the carrying capacity. And k is like some constant. The only thing that really matters in most logistic models is that L value. And so, if we're looking at these expressions, here's what we're going to do. We're going to factor all of these expressions. So I'm going to clear this graph right here. Okay, so if we look at A, we can factor it to look resemblant to this form. Factor it to be like 0.2p times 1 minus, and then this would be p over 100. B would be 0.4p times 1 minus p over, I believe, 50? Or am I dividing wrong? Sometimes I might be dividing wrong. Let me just double check right here. Oh yeah, I'm dividing wrong. For sure. I think that's 200. Yeah. C is going to be 0.8p times 1 minus, I believe it's going to be p over 400. Yeah. D. Okay, so I'm not even going to factor D and E because you see how they have a positive sign here? That's not allowed. So these you can automatically cross out. There has to be this negative sign. Okay, and so, again, like the constants don't really matter. What we're going to look at here are the different L's. And remember, that value is what determines the carrying capacity. And so if we look at our graph, we see that the carrying capacity is 200. So 200 is our L. And so the only answer choice that matches with that is answer choice B right here. And so B is our answer. So big takeaway is know how to read a logistic model and know the equation that models it. But moving on, question 47. Okay, so another calculus one. We're going to see a lot of calculus ones. We have a fourth degree, or we want to find the fourth degree polynomial for f of x equals cosine of x. And using this polynomial, calculate the error when evaluating f of 1.2. Okay. So what you want to know here are is the Taylor series of cos of x. So I'm going to show you two ways to do this problem: the like by hand way and the calculator way. So by hand, the expression for cos of x. Okay, so the way you get like any Taylor series is, so let's just call this like g of x. So if I'm trying to approximate this function f of x, which in this case is like cosine of x, the way I do that is I take the value here at x equals 0. So that would be just, f of x. And so if I do that, this is cosine of x. If I just approximate it based on like setting this function equal to what it's at 1, I would just get like a straight line here. And so that's not really representative of the equation, because it doesn't take into account this like change in value at like a derivative. And so one way we can account for that is by adding the integral of f prime of x dx. And so let's say I know what the value of cosine of x is. It's 1. And I know what f prime of cos of x is at 0. Oh, and this should be 0, my bad. So at 0, the first derivative is 0. So then my equation goes from being like g of x equals 1 to being g of x equals, well, 0x, which is still 0. So that doesn't help us. But let's get more specific. What if I get the second integral of the second derivative at 0? Well, I know what the second derivative is. It's negative 1. I can calculate that using my calculator. And so that's going to be subtracting, or we'll just say like adding negative 1 over, it's going to come out to over 2 factorial. And so basically what a approximation, times x squared, of course. And so what we'd get is we'd get somewhat of a better approximation around 0. And so if we continue this approximation by adding like the third integral of the third derivative, fourth integral of the fourth derivative, and so on, then we'd start to see this approximation become somewhat more similar around 0. And so it becomes a better and better approximation. So we can approximate these functions which, can't be defined by polynomials. We can approximate them with a polynomial. And so that's why Taylor series are useful. And so the Taylor series expression, if we want to get the fourth degree polynomial, so let's just count. Okay, I have this table. I know f of 0 is 1, f prime of 0. If I get all of these derivatives, up to the fourth one, then I can create a fourth degree polynomial that approximates cosine of x. This is going to be 1 minus x squared over 2 factorial plus x to the fourth over 4 factorial. This is approximately cosine of x. And so this is our approximation. And to calculate the error, we're just going to take cos of 1.2 and subtract it by putting 1.2 into this approximation. Like so. And then after calculating that, we'd get and also make sure you're in radians when you do this. Okay, so after typing that, we get an error of about 0.022. Oh, wait. Oh, I typed it wrong. Okay, ignore that. We get an error of about 0.00404. And so that will be answer choice E. Okay, so that was a really rushed explanation of Taylor series. Might not have done the best job. But there's an alternative to like getting all these derivatives and stuff. So that on your calculator, if you go to your calculator page and you go menu 4, C, and then 1, you open this function Taylor, and you have open parentheses. And so what you want to write here is you want to write your function. So in this case, that would be cosine of x. Let me just write it on my end. Then you want to write what your independent variable is, which is x, separated by a comma, right? And then last thing you want to do is write the degree that you want. So we want a 4th degree polynomial, so we're going to write 4. After clicking enter, it gives you the expression of your Taylor series approximation. And so then you can take this output, plug in 1.2 into here, subtract it from cos of x, and you'll get the same answer. So I'd probably do this on the test because it's quicker. So yeah, know the calculator shortcut. All right, so moving on to question 48. Rudy is watching a hot air balloon take off. So let's say Rudy's here. He's watching this hot air balloon take off. Just like a hot air balloon. So he's 500 feet away. And the balloon is increasing at a constant rate of 4 feet per second. We want to know what rate Rudy's angle of elevation is changing. 1 minute, let's say t is equal to 60 seconds, right? After 1 minute of the balloon taking off. It's just traveling directly vertically. So over time, the balloon's gonna be up some distance, and Rudy's gonna have a new angle of elevation here. And we want to know what rate that angle is changing. And so this is a related rates question. So the way you want to do it is first you want to write an equation that models the scenario. So let's call the distance at any point in time the balloon y. So in the beginning y is 0, and at the end y is like some other value. We actually know what that value is. It would be 4 times 60. 4 feet per second times 60 seconds. So after 60 seconds, it's risen 240 feet in the air. Again, Rudy still stays 500 feet horizontally away from the balloon. So we can say that the tangent of theta is equal to y over 50. So you can write like a right triangle here. Call this y, 500, and theta. This equation relates all of these things. And so what we're going to do is we're going to take the implicit, or we're going to implicitly differentiate both sides of this equation. So we'd get dy over dt times 1 over 500 is equal to, well, the derivative of tangent is secant squared theta. We're going to multiply this by d theta dt. So at this point, you got to kind of know how to do implicit differentiation. But you could also have your calculator do it for you, I believe. There's a setting on your calculator to do that. But anyways, so again, we want to know what Rudy's angle of elevation what rate his angle of elevation is changing at this point in time. So that would be d theta dt. This is what we're solving for. Okay, so, excuse me. So, in order to solve for this, we've got to know what secant of theta is, or secant squared of theta is, which means we got to know what theta is. So as we said, after 1 minute, it's gone 240 feet up, and Rudy's still 500 feet away. So if this is theta, then we can get what secant of theta is. You can solve for theta and then plug it into secant of theta, or, you know, so here's what we're going to do. We're going to do the inverse tangent. So theta is going to be the inverse tangent of 240 over 500. Make sure you're in radians. And then we're going to do secant squared of that value. So this is like 0.4475. So we're going to do secant squared of 0.4475. So this value comes out to 1.23. This is equal to 1 over 500 times dy dt. So what's dy dt going to be? Well, dy dt is going to be 4. It already gave us what dy dt is. That's the rate at which y is changing. And it's increasing at a constant rate of 4 feet per second. So now we can solve for d theta dt. So after doing 4 times 1 over 500, all divided by 1.23, we end up with an answer of about 0.0065. So that's going to be answer choice D. And that's the rate at which Rudy's angle of elevation is changing. So know how to work with related rates and doing implicit differentiation. But moving on to question 49. Okay, so consider the region bounded by these three equations. So that's e to the x minus 1 then y equals negative x, and then x equals 4. So to kind of simplify it a bit for y'all, I'm going to draw it as best as I can. So it's going to kind of look like this. And this is scaled a bit. Exponential part's going to look like this. So it's kind of like we've got this this little region here that starts off at 0 and ends at 4. Okay. So the question wants us to know, or wants us to solve for the periphery of this region. So periphery is basically like the perimeter. So we're looking for the perimeter. And so that seems like a complicated thing to do. Okay, well, for one, like these straight line measurements seem fine to get. How do I get the length along this curve? So we're going to need a special formula to solve for that. But first, let's get these two lengths. So it starts from 0 and it intersects here at 4. And again, this is not drawn to scale. If I did draw it to scale a bit more, it would look like this. This is the line, this line right here. That's y equals negative x. So it's kind of like a right isosceles triangle there with a leg of 4. Therefore, this length here is 4 times the square root of 2. Okay, so that's simple enough. And then, then for this long length, that's just going to be this y value of f of x. So that'd be e to the 4 minus 1. That'd be like this part right here. Then we're going to add it with this part right here. It's going to be going 4 under, so we're going to add 4. So the whole length, I have in magenta, it's going to be e to the 4th minus 1 plus 4. So this part's 4, and this is e to the 4th minus 1. Okay, so we've got the lengths of these two straight edges, and so now I need to find the length along this curve. And so the way I can do that is by using this formula. So if I want to get the length of a curve from point A to point B of f of x, I get that length by doing the integral from A to B of the square root of 1 plus f prime of x squared dx. And so all we need to do here is take the integral from 0 to 4, the square root of 1 plus the derivative of e to the x minus 1 is going to be, so after I take the derivative, it's going to be e to the x. So 1 plus e to the x squared dx. If we calculate that integral, comes out to about 54. And so that would be the length across this curved part, 54. So we're going to add up all the parts to get the perimeter. So 4 times the square root of 2 plus e to the 4th plus 3, which is what this comes out to, plus 54 So if I type that all in, I get an answer of about 117. So that's going to be answer choice B. So that's our correct answer. So just know that periphery equals perimeter, and know the formula to get the length along a curve. We're almost done with the calculus portion of math test. Alright, so question 50. When evaluating the integral x squared minus 3 times ln of x dx using integration by parts, the best choice for you is, okay, so integration by parts states that when you have the integral of u dv, that is equal to u times v minus the integral of v du. And so an example where you'd use this, say x times ln of x dx. I want to integrate this. Okay, so the rules to follow are that generally u has to be easily differentiable, and dv is easily integratable. And you get the idea. Okay, so I know what the integral of ln of x is, but I don't really I know what the derivative of ln of x is, but not really the integral. And I know like the integral and the derivative of x. So it's just easier to call my u ln of x, because I can easily get the derivative, and to call my x dv, because I can easily integrate it. And so this integral should be equal to u, or v, which is going to be, if I integrate dv, it'd be x squared over 2, times u, so times ln of x, minus the integral of v, which is x squared over 2, times du, which is the derivative of u is 1 over x, of course dx. So we can get rid of an x here and here. So we're integrating x over 2 dx. So that will be x squared over 4. And so this would be the integral. And so it's important to know integration by parts, but generally, just for this problem, you just gotta know that u is the one that's easily differentiable, and dv is the one that's easily integratable. Okay, so the best choice for u in this case is going to be ln of x. Also, I guess another thing to know is that the u doesn't include dx. Only dv does. And so this question was asking, like, what's the best choice for dv? And that would be answer choice D. Since it's asking for the best choice of u, that would be ln of x. So that means our answer is A. Okay, so moving on. This is the last calculus question. Okay, so number 51. The function f is defined as f of x equals e to the x plus 4x. And g of x is defined as the inverse of f of x. And so we want to know what the value of g prime of 0.5 is. So to get the derivative of like an inverse function at a point, so let's call the inverse g of x, right? The derivative is going to be 1 over f prime of g of x. So this is the formula to know. Okay, so I've got to get g of 0.5. And remember, g of 0.5 is basically asking, so it asks, like, I set f of x equal to 0.5, then what would my x be, right? That's why it's called an inverse function. So I need to solve for my x, so I can plug this equation into my solver. And so I'll get x is equal to about negative 0.1. And so now, what I can do with this is I can plug in this into f prime of x. So I'm going to do 1 over f prime of negative 0.1, and that will get me my derivative of g of x at 0.5. Okay, so f prime, so if this is f of x right here, then f prime of x, we take the derivative. The derivative of e to the x is itself. Derivative of 4x is 4 via the product rule, or power rule. So this is the expression for the for f prime. And so I'm going to plug in negative 0.1 into there. So e to the power of negative 0.1 plus 4. And that should give me my answer. So g of x is equal to this, which is equal to 0.204. And so that will be answer choice D. So make sure that you know this formula for getting the derivative of the inverse function at a point. And so that's all of the calculus questions complete. All right. So now we're moving into the statistics questions. And so for 52 to 53, for question 52, we're going to be talking about the scenario up here. So let's read it. So a local pet shelter thinks the change in the pet food formula this year has increased the mean weight of their population of the cats. Okay, so they think the change, I'm actually going to highlight this. So they think the change has increased the mean weight of the population of their cats. You're going to see why this detail is important. Okay, so last year, the mean weight of the cats was 8.9 pounds. And so the pet shelter took a random sample of 6 of their current cats and found the mean weight to be 9.5 pounds with a standard deviation of 1.2 pounds. All right. So assume the weights of the cats are approximately normally distributed. The pet shelter performed an appropriate statistical test on this data. Okay. So 52 says that the proper null hypothesis is that the mean is, okay, so this right here, okay, so statistics terminology, this symbol mu, that means mean. And this symbol here, which I think is sigma, that's a standard deviation. You could also see that expressed as Sx. You also see mean expressed as x bar. We're not going to go into the differences between those right now, but what you do need to know is, so it's saying the mean is this, that's the null hypothesis. We want to know what the proper alternative hypothesis is. Okay, so what does that mean? So the alternative hypothesis is the one that, like, the people who are organizing the test, that they believe the data represents. Like, it's what they think the data concludes. And so in this highlighted part, we see that they believe that it has increased the mean weight. And it's even shown by the numbers here. We see a clear increase in the mean weight. And so the proper alternative hypothesis isn't that, so this is the null hypothesis. It's like the what the original data says. So it's not that the mean is going to be equal to 8.9 because they believe that the weight has increased. So their alternative hypothesis is that the mean is greater than 8.9. So the only answer choice that shows that is answer choice C. So that would be our proper alternative hypothesis. So remember, the alternative hypothesis is always the one that the data, like they believe the data supports. So moving on. Question 53. So at this alpha value of 0.05, he failed to reject the null hypothesis because the p-value was... Okay, so some terminology. What it means to fail to reject the null means that it's not, like the probability is less than, if you fail to reject, it's greater than this value, which is like your significance. So what we're saying is, if the probability, which is what your p-value is, if the probability is less than this significance level, like if it was like 0.001, well, then that means that that result you got is significant because it's unlikely. So it goes against the standard. It goes against like the normal. Whereas if it's greater than 0.05, well, then you fail to reject the null, meaning that like your alternative hypothesis, it's not like backed up enough. So if like the thing that you measured had like a p-value of like 0.51, that means that was likely to happen. And so basically what this means is that your p-value is going to be greater than this alpha value, which all the answer choices are, so it doesn't really matter. Okay, but how do we calculate the p-value? So the statistics test we're going to run is called a t-test. And so when do you use a t-test? So you use a t-test, okay, so we use when you want to compare a small, and by the way, small means n is less than 30, a small random sample. So use a t-test when you want to compare a small random sample. Okay, so we have to use a t-test because our random sample is only 6, which is less than 30. So we're going to use a t-test. And we're comparing these means, right? The original mean and the new mean. And so the way you're going to run a t-test, you have to do this on your TI-NSPIRE. So what you're going to do, I write this in this little box here. You're going to go menu, 6, comma, 7, and then 2. So menu 6, 7, 2 will get you to t-test. And you want your data input method, because it's going to prompt you with a dialog box. So your data input method should be statistics, or stats. So then after you click enter, then you're going to see this dialog box that prompts. I'm going to write this in another color. You're going to see a dialog box that prompts you for the original mean. So it's going to say mu naught, and then x bar, sx, and then n, and then the alternative hypothesis, which I'm just going to write HA. Okay, so mu naught is the original mean, and x bar is the mean of the sample. So it's your sample mean. And so here you're going to enter in 8.9. And here you're going to enter in the sample mean, which was 9.5. Sx is your measured, your sample standard deviation. So that's 1.2. N is the size of your sample, which was 6. And HA, which is our alternative hypothesis, was just what we had for 52. So it was that our mu is going to be greater than our original mu. Our mean is going to be greater than our original mean. So after typing in all of these values into the dialog box, it outputs a p-value under p-val as 0.1376. So that will be answer choice D. So make sure you know when to use a t-test, how to get to the t-test on your nSpire, and what each of these values that prompts you for, what they mean. All right? So moving on to the next question. So that will be question 54. And I'm going to clear this. Okay. So a gym is starting up and wants to see what weights they really need in order to satisfy their customers. Researcher went to a local gym and recorded the weights used by customers over the course of a week. The researcher found that the weight lifted by a customer was approximately normally distributed. The mean weight, I'm going to say the mean right here, is 110 pounds, and its standard deviation is 32. And we want to know what percentage of customers lifted between 50 and 150 pounds. So this is an example of doing a normal CDF. So you're going to do this on your calculator. So menu 652. So what is a normal CDF? So for something to be normally distributed, that means it looks like a bell curve. I'm sure you guys have seen like IQ bell curves before, or bell curves that represent other pieces of data. So every bell curve that's normally distributed is defined by a mean and a standard deviation, where the mean is the center of the bell curve. The standard deviation is like this constant distance away from the mean. And so on, right? And what the normal CDF does, it's almost like an integral. It's saying between these two values that I give you of, I don't know, A and B, give me the shaded area under the curve. Keep in mind, the area under a bell curve is always equal to 1. So if we just get the area here, it comes out to like a decimal, like say 0.715. Well, that gets us the percent, 71.5. Okay, so after you do menu 652, it's going to prompt you with a dialog box. I'm going to draw this in another color again. So it's going to ask for the lower bound and the upper bound, so see, very similar to an integral. It's going to ask for your mean, and then ask for your standard deviation, and that's it. So inputting these values, okay, our lower bound is 50 and our upper bound is 150, because we want to know between those two values. Our mean is going to be 110, and our standard deviation is going to be 32. So if you type those values into your n-spire, click OK, then it outputs 0.864. And so that right there is 86.4% of values fall between 50 and 150. And so our answer is going to be answer choice A. So know when to use a normal CDF. It's when you want to find this percentage between these two values, given a mean and standard deviation, and how to navigate to that function on your n-spire. But moving on to question 55. A 6-sided die is rolled 5 times. What's the probability it lands on a 4 at least 2 times? So we've got a die. We want it to land on 4 twice, at least twice. So that means we want the probability that it lands twice, that it lands 3 times, 4 times, and 5 times. These are all at least 2. We want to add these all together. And so last time, I think in the previous video, I had said, oh, like the general formula for doing this kind of thing is you're going to do like n choose r times the probability of success raised to the number of successes times the probability of failure raised to the number of failures. And so our n would be, 5 total times. And we'd have to do this like, this case would be like if we were just looking for the probability it landed twice. And then we'd have to add that with the case it lands 3 times, and then 4 times, and so on. And that can take a while. So a simpler way you can do this on your n-spire is by doing what we call a, oh, my bad, I almost wrote the wrong thing. So this is what we call a binomial CDF. All right, and it's going to do all that complex math for us. And so you're going to go menu 65B. Then you're going to get this dialog box. It's going to ask you for n, which is the number of trials, the probability of success, the lower bound, and the upper bound. Okay, so the number of trials, well, we're rolling it 5 times, so that's going to be 5. Probability of success, well, that's 1/6, right? Because probability lands on a 4 on a 6-sided die is just 1 out of the 6 sides. And we want it, this probability, that happens at least 2 times. So our lowest is if it happens twice, and our highest if it happens like all 5 times. And so we're going to type in these values into our n-spire. It's going to output 0.196. And so that's 19.6%. That's answer choice A. So know when to use binomial CDFs. Usually it's characterized by the probability of something happening at least like this many times, given that I roll it a certain n number of times, and how to navigate to that function on your calculator. But moving on to question 56. So this one's a pretty easy question. So right now it says we've got this table with Connor's grades, and it shows or it tells us that they're all weighted evenly. So first we want to know his grade. So we're just going to add everything. So we're going to add everything here and divide by 12, which is the number of grades we have. So we're just taking the average of all of these scores. So you can type that in your calculator page. And so this gives us 87.5, which is answer choice E. So that's the correct answer. Pretty quick question. Okay. And then for 57, if Connor's final exam counts as 25% of his final grade, and he wants to end with a 90, what is the minimum grade he needs if the professor is going to round like an 89.5 up to a 90? Okay. So we're going to do a weighted average. This is like how computers or your registrar calculates your grade, because different things are weighted differently, like quizzes versus daily work versus summative assessments. They all have a certain weight to them. We're going to do this weighted average by doing this. Okay, so all of this stuff right here, well, if the final exam is 25% of his grade, then this stuff is 75%. Okay, and also the formula for weighted average, it's like the weight times I don't know, thing 1 plus weight 2 times thing 2. You just add it all up. And yeah, so, and that'll be equal to your grade. Okay, so 0.75 is our first weight. And as we had calculated in this last problem, that grade came out to 87.5. We're going to add it with the second weight, which is 0.25. And then this thing, we're going to call it x. That's going to be what he needs to get on this exam. And we want this to be equal to 89.5, because then the professor will round it up to a 90. So we'll solve for x. And so we get x is equal to 95.5. So that means he needs a 96 to get the grade he wants, right? Because a 95 won't cut it, so he needs a 96. And so 96 is our answer. So just know how to work with weighted averages. Oops. Okay, so the final 3 questions. Okay, so this table we're going to use for both 86 and 89, 58 and 59. So question 58, what is the linear correlation coefficient? Okay, so you're going to want to go to your lists and spreadsheet. Oh, I can't spell spreadsheet. Spreadsheets page. And so it kind of looks like this. So you're using these two columns, you're going to want to name the top of the first column X and the top of the second column Y. And then down here where cell 1, 2, 3, 4, and 5 and so on are, you're just going to list everything in the X column. So all of these values. And everything in the Y column, which would be all of these values. And then you're going to do, oops. After that, you're going to do menu 4, 1, 3. So that will do a linear regression. Then you're going to get a dialog box. It's going to ask for your X list and your Y list and some other stuff, but all that matters is what you put for your X list and Y list. So you're just going to put what you named them. It should just be X and Y. Then you click enter twice. So after I enter in all of those values, and then do menu 413, then you should get an output that lists a bunch of numbers. So your m would be your slope, your b would be your y-intercept, your r squared is your coefficient of determination, and your r is your correlation coefficient, which is what we want. And so that value came out to 0.965. And so, oh wait, my bad. That's the correlation. That's the coefficient of determination. It comes out to 0.982. Okay, and so that's going to be your answer. That's answer choice B. So know how to work with your list spreadsheets page. And then, still staying with this, question 59. Using the linear regression line, what approximate value of x, or what's the approximate value of x for which y is equal to 60? So here's where this other information comes into play. So specifically, the m and the b, because remember, this gives you your linear equation slope-intercept form. So y equals mx plus b. And so we would just use this. We plug in those values of m and b. We're going to say 60, which is our y, is equal to m times x plus our b, which is 1.875. And all we're going to do is we're just going to solve for x. And so we get that our x is equal to 62. And so that is our answer, 62.0. Right? Don't want to cause any confusion. So yeah, answer choice C is the correct answer. So make sure you know how to do a linear regression on your lists and spreadsheets page, what commands you need to use, and what all of these symbols mean. All right, so moving on to our final question on the test, question 60. All right, so a 5A school wants to determine whether bullying has decreased on campus over the past 10 years. According to a survey conducted 10 years ago, among 300 randomly selected students, 162 students reported experiencing some form of bullying. The survey was conducted again this year, and of the 700 randomly selected students, 340 students reported experiencing some form of bullying. If the null hypothesis is that the proportion of bullied students has remained the same, testing against the alternative hypothesis that the proportion has decreased, what would be the value of the appropriate z statistic for this test? So that's a mouthful, but pretty much the important details is that we had taken a sample before of 300 people, and this proportion, this amount, 162, responded to experience bullying. And then later we took a second survey, and we got this proportion, this 340 students who experienced some sort of bullying. And so right away, that is a sign that we are doing a two proportion z test. So to do this on your calculator, you're going to go to menu 676. And this dialog box will open. So it's going to ask for successes x1. Then it's going to ask for n1. And then successes x2 and n2. And then the alternate hypothesis. And so we can fill all this information in. So number of successes in our first survey was 162 out of a total n of 300. And in our second survey, 340 successes out of 700. And it tells us what our alternate hypothesis is, which is that the proportion has decreased. So that means that P2 is less than P1. And so you'll enter in all of these values right here. And so after you click enter, after typing all this in, you'll get an output that tells you that your z, which is your z statistic, comes out to 1.573. And so that will be answer choice D. And so the main takeaway is recognize when you need to use a two proportion z-test and how to get there on your calculator. And so that was all of the questions on this year's TMSCA 10 math test. So if you have any further questions, please leave them in the comments. What? Did I not fill this out? This was E. If you have any further questions, please ask in the comments section. And I'll be going over some more tests soon. Hopefully I can start having a regular upload schedule again. But yeah, that's the end of the video for today. I'll see you guys next time.